Good afternoon, everyone. I'm Aritra. So this is work done at Samsung Research with my former colleagues Tanakorn, Masoud, and Cesar. This talk is about transactuations, where transactions meet the physical world. IoT systems are everywhere, and people use it for all kinds of purposes like safety, security, and automation. However, they are still early stage and immature with respect to the fundamental properties they provide. In this talk, I will focus on one such fundamental property, that is reliability of IoT systems. I'll talk about one IoT domain called the smart homes. Although the techniques I discuss here can be potentially extended to other cyber physical domains as well. So this is how a smart home looks like. It has sensors and actuators. It receives these physical events, and these events are then sent over the network to the cloud. The applications reside in the cloud. They execute the application logic and then send actuation commands back to the home. Well, everything is not perfect and things can fail. So what could happen is the sensor subsystem might go down, or the sensor or the actuators might run out of battery, there could be a network disconnection or a network partition. So due to this failure, does the implication only cause mere inconveniences? What we found is no, the consequences can be actually much more severe. This is a real world smart home customer who got robbed when he was on vacation. He's upset and dissatisfied with the technology, and he's saying that the motion sensors could detect motion because the logs show motion of the robbers, but the application never sounded the alarm. He lost trust in the system. So let's look at the root cause of this problem. This is a real world application taken from SmartThings smart home platform. It's an intruder detection application. This has an event-based programming model, which is representative of this class of application. It has a handler which is triggered based on physical events captured by sensors and actuators. In this app, the sensor values are read to determine if the motion is of an intruder. It uses heuristics like whether the residents were quiet for a long time and what time of the day it is. It then reads an application state and checks if the alarm is not already active. If it's not, it actuates the alarm and sets the application state active to true. This application state is set because the developer would read this state instead of reading the device itself to reduce battery drainage of the device. So what happens if something goes wrong and let's say the actuation command to the alarm fails, or actuation command is lost, if there is a message loss, or if there is a temporary glitch in the alarm. What happens is now the alarm has been actuated and that has not gone through, although the application state has been updated. This leads to an inconsistency between the physical state and the application state. This inconsistency is irreversible without manual intervention. And even if the intruder moves from one room to another, the alarm would never be sounded by the application. And this is not just a failure that could happen. The device itself comes with a warning that due to RF interference on wireless transmissions, the alarm may not operate as intended. So the fundamental problem in this system is that the failure makes application states inconsistent with the device state. In addition, these applications are event-based and are inherently concurrent. So there could be inconsistencies due to concurrency bugs as well. Let's try to find out how often can these inconsistencies happen. So we identified 3 classes of dependencies in the application logic. These dependencies are basically semantic relationship between the application state and the device state. And these dependencies are vulnerable to failures. That means if they are broken, it might violate the application semantics. By statically analyzing the code for these dependencies, we could identify potential inconsistencies in the smart home applications and thereby find out the undesirable consequences due to these inconsistencies. Let me get into the details of different kinds of dependencies. First is the sensing to actuating dependency, where you can see in this example a carbon dioxide sensor is being read, and if its value is greater than a threshold, fans are being actuated. Now, what happens if there is a failure and the sensor returns a stale value? So, this is returning stale value is there in many of the existing smart home platforms. What happens is now there is an incorrect actuation or a missing actuation. Similarly, if for the sensing to application state update dependency, a thermostat value is being read, and then if its value is greater than a threshold, a software state mode is being set. Again, an incorrect state update could be read elsewhere in the application, and that inconsistency could be propagated elsewhere in the application. Third is the actuating to the app state update dependency, where an actuation is being made and the corresponding software state is updated. Here the software state is tied to the actuation command. So, as you can clearly see, any inconsistency, any failure here would lead to irreversible inconsistency. Our results of static analysis was quite interesting. We analyzed over 182 applications from SmartThings and OpenHab and to open source smart home platforms, and could identify nearly 309 undesirable consequences that arise because of inconsistencies which happen due to failures. So, how can we fix this problem? So, transaction is a very well known programming abstraction that provides the all or nothing semantics and also provides the isolation semantics. On delving deeper, we found that it is impossible to adopt transactions to solve this problem. And this is because of the nature of the IoT solution, IoT environment. Let's see the reasons why transactions is not applicable here. The IoT devices, unlike the software world, cannot be locked because users can still see the intermediate values, and rolling back IoT devices could lead to a poor user experience. For example, the door getting locked and the door again getting unlocked, which the user could see. And in many cases, the actuations cannot even be rolled back, for example, undoing a water dispenser. So, we tailored transactions for the physical world, and we call this abstraction transactuation. Transactuation is a high level programming abstraction that allows the developer to write code in a failure aware way. It provides atomic durability of only application states, as actuations cannot be rolled back. It also provides internal atomic visibility among transactuations, and this prevents several of the canonical concurrency bugs. More importantly, it provides these two invariants. The first is the sensing invariant, which governs executing a transactuation, and the next is the actuating invariant, which governs committing of a transactuation. Let us look at these two invariants in more detail. So, the sensing invariant guarantees that a transactuation executes only when the staleness of a sensor reads is bounded as per a developer specified policy, and the developer can specify two parameters in the sensing policy. One is how much staleness can the application tolerate, and how many failed sensor reads will still preserve the application semantics. An example would be at least one of the CO2 sensor must be available and can be read in the 5 minutes of the triggering event for the application to execute. Let us look at the actuating invariant. The actuating invariant guarantees that a transactuation commits its application states if sufficient number of actuations have gone through as per the developer specified policy, and the actuation policy would have a parameter that how many failed actuations can the application tolerate for it to commit the application states. An example of actuation policy would be commit the application states only if one alarm has been successfully executed. Let's explain this more with a simplified example. So, this is code written by a smart home developer, say, and this is actually real world code, and he is reading carbon dioxide sensors here, and if the value of the sensor reads is greater than a particular threshold, and if he has not already activated the exhaust fans, which is tied to a software state active, he is actuating the fans and setting the software state active to true. So, this is code without transactuations. Now, if he wants to write this code in a failure aware way, he instantiates a transactuation and puts this code in a perform block. Now, he can add a sensing policy to it, meaning that if he can say that if all the carbon dioxide sensors could be read in the last 5 minutes of the triggering event, then only execute the code. He could also add an actuation policy which says commit the application state active to true only if all the actuations in this code have successfully gone through. The actual abstraction is more involved. It has a on success block, on failure block, and also you could chain transactuations together. So, please refer the paper if you are interested in the details. So, this is how the abstraction looks like, but how does it execute under the hood? Let's look at the execution model of our implementation. So, a transactuation starts executing if the sensing policy is satisfied, that if the sensor validation passes, it starts executing. It executes completely in software first, and it defers all the actuations. So, it executes in software and speculatively commits in software. This speculative commit allows transactuations to get a serializable order without rolling back the actuations, as once the final commit phase, that is the actuating phase starts, you cannot roll back the actuations. Then the transactuation enters the actuating phase, which we call the final commit phase, and it finally commits according to the actuation policy. Interestingly, a speculative commit could trigger another transactuation like T2, which goes through the same phase of speculative and final commit, and here it is overlapping the computation of T2 and the actuation in T1, that is the triggering transactuation. A speculative commit could also trigger other transactuations like T3, and some transactuations like T3 might have to wait while its triggering transactuation is finally committing, or any conflicting transactuation is finally committing, that is for correctness. So, I will talk next about the implementation briefly of our execution model. Our implementation is called Relacs, and this runtime is implemented over Azure technology. We use for the applications as well as for system components like the final commit, we use serverless function infrastructure. It is all on serverless functions, and we use specifically Azure functions. For the Relax, for the storage, we call it a Relax store, we use Cosmos DB, and we integrated this system to Samsung SmartThings IoT platform. There are several other interesting details on how we integrate this to the serverless environment, and details of fault tolerance. For example, how we provide the exactly one semantics for transactuations in the serverless environment. So, please look at the paper if you are interested in those details. We evaluated transactuations on several metrics. In the interest of time, I will talk about two metrics here, programmability and the runtime overhead without failures. In programmability, I am showing you several applications here taken from the real world. We re-implemented these applications in Node.js as transactuation is implemented in Node.js. So, the first column is showing the lines of code in the original app, and in the middle column, the developer introduced the consistency guarantees that a transactuation provides, manually introducing lines of code that makes the application complex and increases the lines of code as well. And the third column is the transactuation. It takes similar amount of lines of code as the original application, as it pushes the complexity into the system. Although in certain cases there are applications where transactuations take a lot more code than the original app. This is for correctness, where we chain transactuations together. The details are there in the paper. Let's look at the runtime overhead without failures in the system. So transactuations overall incurs an overhead of 50% over the unmodified, that is the original application without the necessary guarantees. Overall, there is a modest overhead that is incurred by transactuation across all the apps. But again, in certain applications, the overhead is quite high, as you can see in EE1 in this case. And this is again because of the serverless function triggering overhead. Basically, the database update triggering the serverless function has some overhead. There is overhead breakdown in the paper for our evaluation, and there is thorough experimentation with failures as well. So please refer the paper if you are interested in the overhead breakdown. In conclusion, we established a critical reliability issue due to inconsistencies and introduced our abstraction called transactuation that allows a developer to program in a failure-aware way. We demonstrated transactuation's programmability, performance, and effectiveness, and showed that it is a powerful abstraction and execution model. Thank you.
Any questions? All right, so I will ask questions while people are approaching the mic. So I must say that I'm actually scared to death to use those things now, like the smart homes, and because like if CO2 is relying, like the turning on the fan relies on CO2 sensor being accessible through the network, I think something is kind of fundamentally wrong. But my real question is, it looks like the original kind of code samples that you've shown show that people kind of ignore errors by definition, sort of. They don't have this notion of checking for errors every time they try some actuation to go on. And so your proposed model still keeps them out of like this necessity, but helps them to basically handle errors in certain more centralized way. Is that correct?
Yeah, so there are basically sophisticated developers who write these apps who would have to check for errors if he has to write the application in a correct way. And there are some hobbyist developers who write these apps and who would not care about these errors. So this is a generic programming model that we are saying that you could or you should write this in a proper way so that you can avoid this problem of inconsistencies.
Thanks.
Okay, I'm Harshit Gupta from Georgia Tech. So if I understood correctly, you have a condition about how many actuators should succeed in order for the entire transaction to succeed.
Right.
Right. So what happens if it is partially executed? You want to, so those that have already executed are not rolled back. They still remain in the state.
Yes, so we basically just roll back the application state as we cannot, but the transactuation still finally commits. And the rollback of we roll back the application state. So as a result, other transactuations would read the application state which was there before the transactuation started, and that makes this inconsistency go away in a way.
But the physical device is not rolled back. If a door was unlocked, will it be locked again?
So for the ones we have actuated, yes.
They'll be rolled back.
Yeah.
Thanks.
So you mean the ones which have been actuated?
Yes.
No.
Once they have been actuated and some failed because of a failure. So those that have been partially executed, they won't be rolled back.
No, they won't roll back.
But then you roll back the application state.
Application state only.
So then there's an inconsistency, right? Because the door has been unlocked, but now you roll back the application state to it saying that it's locked.
There is an inconsistency in the state, but if another application is reading the software state, then it would function correctly.
Right.
Yeah.
Thanks.
Stefan Bukur from Google. I was wondering whether the applications used for the evaluations are representative for the complexity and the size of the code base of a real-world IoT device, something that used in the original example, somebody had been robbed and so on, and whether do you foresee any issues with refactoring like a larger code base to use transactuations?
Sorry, if we faced any issues.
So do you think it would be easy to refactor a larger code base than the ones that you showed to use transactuations? So you use something like 100 or 200 lines of code. I'm imagining
Yes.
real applications may be much larger than that. Do you
Well,
think it would
the
be-
smart home applications, these are real applications, and they are usually hundreds of lines of code because these are rules, although they are event based and have complex concurrency primitives in them. But I think the technique is basic and can be extended to other cyber physical domains having a larger code base.
Okay, thank you.
Yeah, I'm sorry, we actually don't have more time, so let's take this offline. And thanks, the speaker.
Thank you very much.